Next is methods of purification of organic compounds. See, in the concerned chapter, when you take up the fundamentals of organic chemistry, so far discussed area and the last portion of the chapter is purification and characterization. When you get a impure sample of matter naturally, many times naturally obtained sample will be impure. How you are going to characterize that material? Characterize means, first of all, you have to make it pure matter. Then you have to identify what all elements are present. Then you have to identify what is the percentage of that elements. Then you need to find the empirical formula, molecular formula, various tests. Finally, we try to identify what is the compound we got. This is called purification and characterization. Imagine you get a unknown biomolecule system. You first make it pure. Then qualitative analysis, detection of elements. Then quantitative analysis, estimation. Then finding empirical formula, molecular formula, molar mass, identifying the final compound. That is what whole referring in purification and characterization. But in the current topic, we discuss a few methods of purification techniques. We discuss detection of certain elements. We discuss estimation of the elements. That is what we do in the chapter. So, purification and characterization. Various methods commended are sublimation, crystallization, distillation, differential extraction, chromatography, somewhat in detail. That is what happening in the purification area. So, first of all, sublimation. I am sure all of you know sublimation is done in sublimable material with non-volatile impurities or non-volatile material containing sublimable impurities. That is what separated by sublimation technique. For example, camphor containing impurity. All of us know how to purify it. Camphor is volatile in nature and it can undergo sublimation. Right? So, the material containing volatile impurity or non-volatile impurity, vice versa, a volatile material with a non-volatile impurity or non-volatile material with a volatile impurity can be separated easily by sublimation. You just heat it, the sublimable object will be leaving the material. Suppose you have a material to be refined is volatile material containing non-volatile impurity. You heat it and collect the vapors, take to another chamber and condense it. You get back the material. So that is sublimation technique. Crystallization. We can see crystallization, normal crystallization technique. We take the sample to be refined, taken in a round bottom flask and heating, and you can find the vapors will be coming through the outlet and passing through a condenser. This is a condenser and the condensing materials will be liquefied and you can separate it. So components containing A and B having sufficient difference in the boiling point. So the mixtures containing A and B having sufficient difference in the boiling point separated by normal distillation techniques. So either A or B, which is more volatile, having low boiling point, will be coming first and can be separated in the vessel. So that is normal distillation technique. While there is a fractional distillation, this is fractional distillating column. Suppose there are 3-4 components with a close boiling point. Suppose A, B having sufficient difference in the boiling point, you can conduct normal distillation. Suppose the boiling point is very close to each other, it is separated by fractional distillation. So imagine there is a mixture containing A, B, C, D, close boiling point. This is a mixture containing A, B, C, D in the vessel having no sufficient difference in the boiling point. Slight difference in the boiling point. We heat it, the vapors will start passing through this fractionating column. Heavy fractions will condense and come back to the vessel, while the lighter fraction will reach to top first. out of A, B, C, D, suppose the volatility, relative volatility is A, B, C, D like that. That means relatively D is more volatile. Just imagine. That means D has got a low boiling point relatively. So vapors of D will be coming first and condensing and will be collected over here. Once all the D separated, then C will come. While all the C is separated, then B will be coming. A will be coming only last. So step by step separation, very famous in the petroleum refining. Petroleum refining is done by fractional distillation, right? That is fractional distillation. This is one fractional distillating column, or you can have another fractional distillating column as you find here. This is a fractional distillating column, bubble plate column. This is simple packed column. Such a column is used in a commercial way in refining of petroleum, right? There is another one which is called distillation under reduced pressure. That is vacuum distillation. Distillation under reduced pressure. I am sure all of you agree, the boiling point of a liquid is influenced by external pressure. When the external pressure decreases, boiling point will decrease. So what we do is, suppose you have a heavy boiling liquid, suppose you are having a higher boiling liquid and tough to boil it. What you can do is, you attach with a vacuum pump. You attach the entire system with a vacuum pump and you reduce the pressure. When you reduce the pressure, boiling point of the liquid will be reduced and it can boil easily. It can boil easily, and that is called a vacuum distillation or distillation under reduced pressure. The refining of or purification of hydrogen peroxide done by distillation under reduced pressure, because it's not possible to boil hydrogen peroxide because it will decompose. The decomposition temperature of hydrogen peroxide is somewhat below the boiling point. So what will happen? You can't boil it. So there are certain substances which you can't boil it. Suppose you try to boil it, it will decompose. So what do? We decrease the boiling point by decreasing the pressure. It is called a distillation under reduced pressure. Glycerin, very high boiling point. So you have to heat up to that temperature. You reduce the pressure, it will be boiling pretty fast. That is distillation under reduced pressure. There is one more method, steam distillation. That is also an effective method, steam distillation. It is distillation done with the help of steam. You see, certain substances which are steam volatile can be distilled by steam distillation. Like material like aniline. Aniline is steam volatile. The vapors of aniline and steam are identical character and they are immiscible substances. So substances to be handled for steam distillation should be immiscible with each other and they should be steam volatile in nature. They should have identical vapor characters. So what happens is, we have a liquid which is steam volatile, we heat it, parallelly we heat water and the vapors steam. Steam is pumped all the way through this into this chamber. So this chamber will contain vapors of steam and the vapors of this liquid. And that pressure, when becomes equal to external pressure, the liquid boils. The pressure of liquid, the pressure of steam, when becomes equal to 1 atm, the liquid will boil. That means the liquid can boil pretty fast because it has got a contributing pressure due to steam. The steam also contribute towards the total pressure of the system. You know what is the boiling temperature? Boiling temperature is the temperature at which vapor pressure of a liquid becomes equal to external pressure. Here, this and this together when become equal to external pressure, the liquid starts boiling. That means the liquid will boil pretty fast. What is the theory involved? What is the principle involved? According to which law this can be explained? Dalton's law. Dalton's law of partial pressures. The total pressure of a mixture of two or more non-reacting gases. So these liquid vapors and H2O vapors should not be reacting with each other, where you can apply steam distillation. So normal distillation, sublimation, normal distillation, simple distillation, fractional distillation, distillation under reduced pressure, steam distillation. Okay. What next? There is a topic solvent extraction. Solvent extraction. Look at solvent extraction. Very simple method. This is before extraction and this is after extraction. You see, you have an organic compound in aqueous layer and you want to separate it. An organic compound you have in an aqueous layer and you want to separate it. What do? You add a suitable solvent. You take the entire system in such a funnel and you add a suitable solvent on top of this. What will happen is this organic compound is more willing to dissolve in organic layer. So organic component from this area will be migrating to organic solvent. Now the organic compound is dissolved in solvent layer and you get water separated. Now open this funnel, water will be removed and you get the organic component in concerned solvent. That's a way to separate solvent extraction. Solvent extraction you can do step by step also. Okay. And now the most important discussed area, chromatography. Chromatography. There is different types of chromatography, adsorption chromatography and partition chromatography. First of all, adsorption chromatography. The principle behind the chromatography is relative adsorption. You see, this is adsorption chromatography. Example, column chromatography. This is called column chromatography. See, we are taking a column which is filled with an adsorbent, a stationary phase, alumina or something like a stationary phase silica materials are filled in that column, which is taken as a adsorbent material. And now the material to be separated. Imagine you have a mixture ABC to be separated. You have a mixture A plus B plus C to be separated. That is added onto this column. And now a suitable solvent is added. Now you see what happens. The solvent will drain down. As the solvent comes down, it will take ABC also down. So along with the solvent, ABC comes down. And now after some time A is separated because A got adsorbed over here. B and C comes down. After some time B got adsorbed and C comes down. You can see ABC will be obtained as three different layers according to their relative adsorption tendency. Can you tell me out of ABC in the diagram which has got a greater adsorption tendency? Is it A, B or C? Which got a greater adsorption tendency? It is A. A got greater adsorption tendency than B than C because A adsorbed first, then B and then C. C adsorption tendency is minimum and is coming down, while A adsorbed straight away at first. Hope you get the point. This is column chromatography. While we have another technique called thin layer chromatography, TLC, we call it as TLC, thin layer chromatography. And here we have thin layer chromatography explained here. This is a TLC plate. This is a TLC plate, adsorbent coated on a glass plate. This is the glass plate, all of you know. And there is a baseline drawn in the glass plate. And we have taken a suitable solvent over here. And the sample to be separated, A, B, C, is spotted in this place. And now the entire system is immersed into that, introduced into that solvent inside the jar. Now you can see this solvent will start migrating through the surface of the plate, which is coated with adsorbent. The solvent molecules start migrating through the surface of the glass plate where the adsorbent is coated. Now the solvent moves and it reaches over here. It will take away the sample ABC along with the solvent. So along with the solvent which is moving, ABC will move to top. Now what is going to happen? This is the baseline. Here we had the spot A, B, C. Now, as the solvent move up, ABC move up along with the solvent. Now, somewhere here, A is separated. B, C go to top. Somewhere here, B is separated. And somewhere here, C is separated. While the solvent travel all the way up to this. All the way up to this, the solvent is traveling. While the spot ABC is striking somewhere in between as separate spot. Suppose you have ABC, you will get one spot here, one spot here, one spot here, ABC separated. Right? Now, the distance traveled by the one component that can be marked as X, and the distance traveled by the solvent that can be taken as Y, and then you have RF factor of A. RF factor of A equal to X by Y, where X is distance moved by the substance from baseline, X, distance moved by the solvent from the baseline, Y. A very important terminology, all of you know. I'm just reminding you. RF factor, retardation factor. What is retardation factor? The height traveled by the component from the baseline divided by the height traveled by the solvent. That is called RF factor. So, which has got a greater RF factor, A, B, or C? Which got a greater RF factor? RF factor for A, this height divided by this height. That is RF factor for A. What is RF factor for B? RF factor for B will be this height divided by the height traveled by the solvent, which is a fixture. What about RF factor for C? This height from the baseline, this height divided by the distance traveled by the solvent. That is RF factor for C. So, what is the order of RF factor for ABC? In the diagram, A low RF factor, then B, then C. C got high RF factor. Now, again the question comes. What about the relative adsorption tendency? Which got a greater adsorption tendency? A, B, or C? It is once again A. A has got the maximum adsorption. Then B, then C. Because A struck first. A stopped traveling first. It is adsorbed here. B adsorbed here. And C has traveled maximum away from the baseline. And the adsorption tendency for C is minimum, adsorption tendency A maximum, because this adsorbed first. So we can have a relation with the RF factor and adsorption. Greater the RF factor, lower the adsorption. Lower the RF factor, easier the adsorption, greater the adsorption. That's a very important point concerned to the adsorption. We have column chromatography and thin layer chromatography. In a similar context, we can have paper chromatography, which is partition chromatography, where we have a wet paper soaked with water or aqueous medium or any suitable solvent will be used as a adsorption surface. And the procedures are quite the same, all of you know. Procedures are quite the same. Instead of a thin layer sheet where adsorbent coated, we are using paper. And here, both the mobile phase and stationary phase are liquids. In paper chromatography, the stationary phase is the wet aqueous medium or solvent medium applied over the paper. And mobile phase is also a liquid component. Both are liquid component. And procedures are quite similar, whatever we discussed like in TLC. That is partition chromatography, paper chromatography. Is it clear? So, the various purification techniques: sublimation, simple distillation, fractional distillation, then steam distillation, distillation under reduced pressure, right? And then solvent extraction, and then chromatography. Chromatography, adsorption chromatography, and partition chromatography. In adsorption chromatography, column chromatography, thin layer chromatography, and paper chromatography. A very important terminology: retardation factor, RF factor. Is it clear? Is it clear? Next topic is detection of elements, qualitative analysis. Qualitative analysis. Qualitative analysis, that is detection of elements. Detection of elements. First of all, carbon and hydrogen. Detection of carbon and hydrogen. All of you know carbon hydrogen detected by Liebig's combustion method. Liebig's combustion method. You are given with a organic compound and we convert all the carbon content in the compound in the form of carbon dioxide. So we do the appropriate procedures, appropriate chemical reactions, particularly heating with the copper catalyst. Heating with the copper oxide catalyst, all carbon content in the organic compound converted to carbon dioxide in the environment free from moisture, in the environment free from carbon dioxide. So the entire carbon content in the organic compound we are converting to carbon dioxide, and that is tested using lime water test. Test using lime water test. I am sure all of you know what is lime water test. The obtained gas will be passing through the lime water. If it turns milky, we confirm presence of carbon dioxide. So if we get a milkiness, if we get a milkiness when passing through lime water, calcium hydroxide, we can confirm CO2 is present, hence we can confirm carbon is present. So carbon in an organic compound is tested by lime water test. In what form? Carbon dioxide form. What about hydrogen? Hydrogen is tested in the form of water. Hydrogen is tested in the form of water. Once again, same procedure. The organic compound is strongly fused with the heated with the copper oxide catalyst, and the all carbon content will be converted to carbon dioxide, and we remove all other oxides which probably may be present by using suitable chemical reactions. For example, passing through potassium dichromate solution, it will remove all SO2 content if present. Heating with the copper mesh, it will remove all nitrogen oxide content if present. Like that. Okay. So we get the products obtained, and if that product contains CO2, you will get a lime water test. We can confirm carbon. And H2O can be tested using anhydrous copper sulfate. All of you know anhydrous copper sulfate, which is colorless in nature. Anhydrous copper sulfate is colorless in nature, through which these vapors will be passed through, and the anhydrous copper sulfate will turn hydrated copper sulfate, which is blue in color. All of you are aware of. You get CuSO4 5H2O, that is blue vitriol. So presence of carbon tested by lime water test in the form of carbon dioxide. Presence of hydrogen tested by anhydrous copper sulfate turning blue in the form of water, we test hydrogen. This is called the Liebig's combustion method. Now it is testing of halogens. Now it is testing of halogens and nitrogen and sulfur. They all done using Lenzini's test. Nitrogen, sulfur, halogen. It is conducted by Lenzini's test. Lenzini's test. What is Lenzini's test? The organic compound is fused with the metallic sodium. The given organic compound is fused with the metallic sodium, and the covalently bonded nitrogen, sulfur, halogen are converted to ionic forms of respective sodium compound. We get nitrogen along with the carbon along with the nitrogen, we get sodium cyanide, and sulfur you get sodium sulfide, and halogen you get sodium halide. Sodium halide in particular, sodium chloride, sodium bromide, and sodium iodide. We are unable to test for fluorides, as fluorides are it's not been able to get a precipitation of fluorides. So test is limited to chloride, bromide, iodide only. So all carbon, nitrogen converted to cyanide form, all sulfur content here converted to sulfide form, all halogen content here converted to halide form. So covalently bonded elements are converted to ionic form, and we have a filtrate containing sodium cyanide, sodium sulfide and sodium halide. Now we are going for the test. How the cyanide is tested, how nitrogen is tested. It is in the form of Prussian blue. Now we have sodium. This is called a Lacini extract. This solution containing this is called a Lacini extract. Lacini's extract, also called a sodium fusion extract. Sodium fusion extract preparation is number one. How to prepare that? The organic compound is fused with the metallic sodium, and the obtained material is got as a filtrate solution, which may contain any of this, which can be subsequently tested for its existence, and that solution we call it as Lacini extract or sodium fusion extract. Now this sodium fusion extract is taken for test. How it is testing for cyanide? We take Lacini extract, we take 2-3 ml or 5 ml of Lacini extract. Okay. Now it is added with a freshly prepared ferrous sulfate solution. It is added with a freshly prepared ferrous sulfate solution. So take in a test tube, take some Lacini extract solution, add some freshly prepared ferrous sulfate solution, add some concentrated sulfuric acid. If you get a special type of blue solution, that is so called Prussian blue, it's a confirmatory test for nitrogen present as cyanide. The final result product obtained is Fe4, FeCN 6 times whole thrice. We call it as Prussian blue. Prussian blue. That's a confirmatory test for cyanide. What is happening is Fe2 plus interact with Cn minus. You get a complex. Okay. So you get ferrocyanide complex. That again react with the Fe3 plus. Fe2 plus in presence of sulfuric acid converted to Fe3 plus, and that further react to form the final complex so called Prussian blue. This is Prussian blue. Fe4, FeCN 6 thrice. Iron 3, hexacyanidoferrate 2. This iron is plus 3 state. This iron is plus 3 state, and this iron is plus 2 state. It is ferrocyanide. Ferrocyanide, or systematic name will be iron 3 hexacyanidoferrate 2. That is the confirmatory test for cyanide, confirmatory test for nitrogen in Lacini extract. What about sulfur? How sulfur is tested? Sulfur is tested again using Lacini extract. We take 2-3 ml of Lacini extract and we add lead acetate. We add lead acetate. Lead acetate is added with the acetic acid into Lacini extract. If you get a black product, if you get a black precipitate, you can confirm sulfur is present. What is happening? Lacini extract suppose contains sodium sulfide. It is interacting with lead and you are getting black lead sulfide precipitate. Formation of black lead sulfide confirms the presence of sulfur in the form of sodium sulfide in Lacini extract. Or for sodium, you have another test. What is that test? The Lacini extract is treated with sodium nitroprusside, Na2 FeCN 5 times NO. This is sodium nitroprusside. The name of the product is, name of the reagent is sodium nitroprusside. This sodium nitroprusside interacting with the Lysine extract which may contain Na2S, you will get a violet colored product. Formation of violet colored product. What is a violet colored product obtained? Very simple. Na4 FeCN 6 times NOS. This is sodium nitroprusside and this is sodium thionitroprusside. Sodium thionitroprusside, violet colored product. That is the confirmatory test for sulfide. So sulfide you can have two tests. One with the lead acetate giving black product and one with the sodium nitroprusside giving violet product. And the violet product obtained is sodium thionitroprusside. Or sulfur with the nitrogen, you can get a combined test. Sodium thiocyanate. Sodium thiocyanate, you can have a combined test for nitrogen and sulfur together. And that is giving a blood red color. Combined test for sulfur and nitrogen together. Sodium with carbon, nitrogen, sulfide, you get thiocyanate. Thiocyanate in the form of thiocyanate. You will get a blood red colored complex by adding ferrous sulfate. You take Lysine extract and add ferrous sulfate. If you get a blood red coloration, you can confirm sulfur and nitrogen together present. And this is the confirmatory test causing complex FeSCN2 plus. And if you don't want combined test for sulfur and nitrogen, you can do the individual test. You add extra sodium. During Lysine extract preparation, add excess sodium and heat strongly. If there is thiocyanate formed, it will be converted to cyanide and sulfide and you can have individual test. No issue. Okay, so nitrogen tested as Prussian blue, sulfur tested as black lead sulfide, violet sodium thionitroprusside, and combined test blood red coloration with the ferrous complex. Now it is about halogens. What about the halogens test? How halogens are tested? We take Lysine extract. First it is boiled with the nitric acid. So that if there are some sodium sulfide present, may not interfere in the test and create a confusion. We want to remove sodium cyanide, sodium sulfide from the Lysine extract if present so that we can avoid confusion. So to remove sodium sulfide, to remove sodium cyanide if present, we boil with the nitric acid. And upon boiling, suppose NaCN present, it will be removed as HCN. Suppose sodium sulfide is present, it will be removed as hydrogen sulfide. So their involvement is removed. And now we have NaX. NaX can be further tested with a silver nitrate solution. Suppose you are getting a white precipitate. Which is soluble in ammonium hydroxide. You can confirm chlorine is present. Because silver nitrate react with suppose it is NaCl, Cl minus interact with Ag plus, you get a white precipitate AgCl which is soluble in ammonium hydroxide. Okay. Meanwhile, suppose it is NaBr, you will get a off-white precipitate. Off-white precipitate is obtained, pale yellow. That is AgBr precipitate, which is partially soluble in ammonium hydroxide. And what about it is NaI? What about if it is NaI? You get yellow precipitate AgI. That will be yellow precipitate AgI, which is insoluble in ammonium hydroxide. So white precipitate soluble in ammonium hydroxide, chlorine is detected. Pale yellow precipitate partially soluble in ammonium hydroxide, bromine is detected. Yellow precipitate insoluble in ammonium hydroxide, iodine is detected. So NaX with the silver nitrate, you get AgX, AgCl, AgBr, AgI. So that is about the test for halogens. And finally, a detection test for phosphorus. Finally, a detection test for phosphorus. How phosphorus is detected? You see, this is the procedure which you can find. The given organic compound is oxidized using, fused using some oxidizing agent like sodium peroxide. The given organic compound is heated with a sodium peroxide. What will happen is the phosphorus content in the organic compound will be converted to sodium phosphate. You will get the organic compound containing phosphorus. It will be converted to sodium phosphate. So from the organic compound, phosphorus content will be converted to sodium phosphate. So let me write that reaction. We are taking some organic compound fused with a sodium peroxide. There, the phosphorus content in the organic compound will be converted to sodium phosphate. Now what we do, this is treated with the nitric acid. You get phosphoric acid. Now we are adding a special reagent, ammonium molybdate. Ammonium molybdate, don't forget the formula. NH4 twice MOO4. We are adding ammonium molybdate, and that if produces a yellow precipitate or yellow colored product. Upon adding this, if you are getting an yellow colored product or yellow precipitate, you can confirm phosphorus is present, and that is due to ammonium phosphomolybdate, NH4 thrice PO4 12MOO3. So phosphorus detected in the form of yellow precipitate or yellow colored product, ammonium phosphomolybdate. What all things we are doing? We take the organic compound containing phosphorus if fused with oxidized using sodium peroxide or some suitable oxidizing agent and is converted to sodium phosphate. Treated with the nitric acid, you get phosphoric acid, and that further interacting with the ammonium molybdate, you are getting ammonium phosphomolybdate, NH4 thrice PO4 12MOO3. Understanding this formula itself is very important pertaining to a direct question. And that's all regarding the detection of elements. What all the detection we have seen? Carbon detected as carbon dioxide lime water test, hydrogen detected as water with the copper sulfate turning blue, and then nitrogen sulfur halogen Lacini's test, and now phosphorus in the form of ammonium phosphomolybdate. Right? Next is quantitative analysis. Quantitative analysis. See, in quantitative analysis, we are trying to do the estimation, percentage of various elements available in a compound. That is estimation, quantitative analysis. That is the last part of the chapter. So let's see one by one. First of all, estimation of carbon and hydrogen. Estimation of carbon and hydrogen. Carbon and hydrogen are estimated by Liebig's combustion method, already commented. Carbon is estimated as carbon dioxide. Carbon estimated as carbon dioxide. You see, we are taking a known weight of organic compound, say m gram, and the entire carbon content in the organic compound is converted to carbon dioxide, and we find the weight of carbon dioxide obtained by suitable methods. All of you know carbon dioxide can be absorbed in KOH, right? Carbon dioxide may be absorbed in KOH. So using the suitable experiments, the given organic compound, the entire carbon content is converted to carbon dioxide by combustion with the copper oxide catalyst, followed by subsequent chemical reactions for removing the entire other oxides like oxides of nitrogen, sulfur, etc. right? And the process is done in an environment free with moisture and carbon dioxide. And the entire carbon content in the organic compound, which we take m gram organic compound, the carbon content is converted to carbon dioxide, and we get w grams of carbon dioxide we get. Now you can do the estimation calculation like this. All of you know 1 mole CO2 contain 1 mole carbon. 1 mole CO2 means 44 gram CO2 contain 12 gram carbon. Therefore, 1 gram carbon dioxide contain 12 by 44 gram carbon. Therefore, W gram carbon dioxide contain 12 by 44 into W gram of carbon. Now you see this much carbon we have in this much organic compound, because this carbon dioxide we get from m gram organic compound. M gram organic compound contain W gram carbon dioxide, and that W gram carbon dioxide contain this much of carbon. That is, this much of carbon is present in m gram organic compound. So you can have a direct relation now. It is m gram organic compound contain 12 by 44 into W gram carbon. Therefore, 1 gram organic compound contain 12 by 44 into W divided by m gram carbon, and hence 100 gram organic compound contain, that is the percentage, 100 gram organic compound contain 12 by 44 into W by m into 100. And this is the percentage of carbon. Percentage of carbon is equal to 12 divided by 44 into weight of carbon dioxide divided by mass of organic compound into 100. This is the formula. What is 12? 12 is the carbon weight. 12 is the carbon weight. What is 44? 44 molar mass of carbon dioxide. What is W? Mass of carbon dioxide obtained in the experiment. What is M? Mass of organic compound. So if you take m gram organic compound, and if you are getting W mass of carbon dioxide, the percentage of carbon will be 12 by 44 into W by m into 100. I repeat, this is weight of CO2 obtained in the experiment from this much weight of organic compound. Is it clear? I hope it is clear. How we got the derivation? How we got the derivation? 1 mole CO2 contain 1 mole carbon. 1 mole CO2 contain 1 mole carbon. 44 gram CO2. 1 mole CO2 means 44 gram CO2. 44 gram CO2 contain 12 gram carbon. 1 gram CO2 contain 12 by 44 carbon. W gram CO2 contain 12 by 44 into W gram carbon. This we are getting from this, and that we are getting from this. Therefore, m gram organic compound contain 12 by 44 into W gram carbon. And 1 gram organic compound contain this much carbon. 100 gram organic compound, that is percentage of carbon, equal to this. I hope it is pretty clear, right? In a similar way, we can understand estimation of almost all elements. How to find the estimation of hydrogen? How to evaluate the estimation of hydrogen? Very simple. We take m gram of organic compound, and the entire hydrogen content we are converting into water. The entire hydrogen content we are converting into water, and imagine you are getting x gram water. So m gram organic compound, upon experimental analysis, the entire hydrogen converted to x gram water. So what is the percentage of hydrogen? Similar formula. What is the percentage of hydrogen? 2 by 18 into x by m into 100. A similar formula, similar calculation. What is 2? Weight of hydrogen in water. What is 18? Molar mass of water. What is X? Weight of water obtained in the experiment from m gram organic compound. Same dicto formula. Dicto formula. So that is estimation of carbon hydrogen, Liebig's combustion method. What about estimation of other elements? Let us talk about estimation of halogens. Halogens are estimated by halogen, sulfur, phosphorus, etc. are estimated by Carriers method. They are estimated by Carriers method. Carriers method. For example, estimation of halogens. Estimation of halogens. Chlorine estimated as AgCl. Chlorine estimated as AgCl. So what will be the formula? Percentage of chlorine is equal to 35.5 divided by molar mass of AgCl 143.5 into X by M into 100. Similar formula. Similar formula. What is 35.5? Weight of chlorine in AgCl. What is 143.5? Molar mass of AgCl. 108 silver, 35.5 chlorine. Molar mass of AgCl, 143.5. And X. X is the weight of AgCl obtained in the experiment from m gram organic compound. This is the weight of AgCl obtained from m gram organic compound. Similar formula. Where bromine estimated as AgBr. So what is the formula for percentage of bromine? It is 80 divided by 188 into X by M into 100. Now what is 80? 80 is the mass of bromine. 188 molar mass of AgBr. X weight of AgBr obtained from m gram organic compound. Dicto formula. Similar formula. If you understand one formula, the other formula is very simple. So carbon estimated as carbon dioxide, hydrogen estimated as water, chlorine estimated as AgCl, bromine estimated as AgBr. What about iodine? Iodine estimated as AgI. So what is the percentage of iodine in organic compound? It is 127. Iodine atomic mass, isn't it 127? Yeah, 127. 127. So what is the molar mass of AgI? 127 plus 108. 235 into X by M into 100. This is atomic mass of iodine. This is molar mass of AgI. This is weight of AgI yellow precipitate obtained from m gram organic compound. Similar thing. Right? So all are coming identical way. All formulae coming identical way. What about sulfur? Sulfur is estimated as barium sulfate. Sulfur is estimated as barium sulfate. So how is the formula coming? Percentage of sulfur equal to sulfur atomic mass 32. 32 divided by 232 into X by M into 100. 32 is weight of sulfur. 233 molar mass of barium sulfate. X the weight of barium sulfate obtained from m gram of organic compound. Weight of barium sulfate obtained from m gram organic compound. That is the formula. So carbon as carbon dioxide, hydrogen as water, chlorine AgCl, bromine AgBr, iodine AgI, sulfur as barium sulfate. Now, what about phosphorus? Phosphorus we do in two ways. Phosphorus can be estimated as number one, magnesium pyrophosphate Mg2P2O7. This is number 1, where the formula will be percentage of phosphorus is equal to, there are 2 phosphorus, it is 31 into 2 divided by molar mass of this 222 into X by M into 100. So 31 into 2, 62. That is mass of phosphorus in the molecule. 222 molar mass of magnesium pyrophosphate. X, the weight of magnesium pyrophosphate obtained from m gram organic compound. Number 1. And there is one more. One more we were discussing few minutes back. And phosphorus can also be estimated as ammonium phosphomolybdate. NH4 thrice PO4 dot 12MOO3. Ammonium phosphomolybdate, that is another form where phosphorus is estimated. We are discussing few minutes back. And the percentage of phosphorus will be, there we have one phosphorus, 31 divided by 1877 into X into M, X by M into 100. What is 31 mass of phosphorus? One phosphorus in the molecule. 187 molar mass of this compound. X, the weight of this compound obtained from m gram organic compound. So all the formula typically similar. Percentage of carbon, hydrogen, chlorine, bromine, iodine, sulfur, phosphorus. Carbon as carbon dioxide, 12 by 44. Hydrogen as water, 2 by 80. I am referring the point of difference. The rest all identical parameters. Chlorine AgCl, bromine AgBr, iodine AgI, sulfur barium sulfate, phosphorus, 2 forms. Magnesium pyrophosphate and ammonium phosphomolybdate. What about estimation of nitrogen? What about estimation of nitrogen? Nitrogen estimation is typically somewhat different, Nitrogen estimated in 2 different forms. Nitrogen can be estimated in the form of Dumas method. In Dumas method, nitrogen estimated as N2 gas. N2 gas. The given organic compound containing nitrogen is converted to N2 gas by suitable chemical reactions. And that is absorbed and that is retrieved from the system, and we find out the volume of nitrogen gas obtained from the given compound, organic compound, definite mass of organic compound. We find the volume of nitrogen gas which actually we get in the experimental condition, and we convert into volume at STP. So we take m gram of organic compound, the entire nitrogen converted to N2 gas, and we find the volume of nitrogen gas obtained at STP, V milliliter at STP. Do we get actually at STP? No. Do we get a pure N2 volume? No, we get a wet gas. So we find out the volume of the dry nitrogen gas first, and that too will be in experimental condition. That can be converted to STP condition. P1 V1 by T1 is equal to P2 V2 by T2. We can convert into STP condition. So the organic content, nitrogen content in the organic compound taken m gram, quantitatively converted to volume of N2 gas at STP. Now the formula is almost similar. What is the formula? Percentage of nitrogen will be, yes, 28 divided by 22,400 or 22,700 according to new standards into V divided by M into 100. See, what is 28? 28 is mass of N2. What is 22,400? 22,400 is nothing but molar volume. Molar volume. According to new standards, it will be 22,700. Old standards, 22,400. What is this? Volume of N2 gas in milliliter obtain that STP from m grams of organic compound. V is volume of N2 gas obtained at STP from m gram organic compound. Is it clear? This is Dumas method of estimation of nitrogen. There is one more method for estimation of nitrogen. I think this is clear. We take m gram organic compound. The nitrogen content in the organic compound is by suitable technique converted to N2 gas. And that N2 gas, we find the volume of N2 gas obtained at STP. So these two data are required. And then what is the formula? Percentage of nitrogen is equal to 28 divided by 20 to 400 V by M into 100. So the formula is much similar, but here it is volume term, there it is mass term. That is the difference. While the percentage of estimation of nitrogen in another more method, that is entirely different. Geldahl's method. This is Dumas method. Last, percentage of nitrogen by Geldahl's method. Geldahl's method, estimation of nitrogen. Here nitrogen estimated as ammonia. Here nitrogen is estimated as ammonia. Here you see what we do is we take the organic compound, say m gram, and the entire nitrogen content is converted to ammonium sulfate by fusing with the sulfuric acid, using copper sulfate, using potassium sulfate as catalytic substances. The entire nitrogen content from organic compound we convert into ammonium sulfate. Now this ammonium sulfate is digested with alkali. This is digested with alkali and there you get ammonia gas. That ammonia gas we are pumping into a standard solution of sulfuric acid. This we are pumping into an excess of standard solution of sulfuric acid having molarity M, volume V. So this ammonia we are pumping to this. So we take an excess of standard sulfuric acid solution. This is H2SO4 solution having molarity M, volume V, and that we take excess. To this we are pumping ammonia. Now what is going to happen? That ammonia will be neutralizing some amount of sulfuric acid. Right? As we have taken excess quantity of sulfuric acid, some quantity of sulfuric acid will be neutralized by ammonia. So how much ammonia neutralizes sulfuric acid? To know that, the remaining ammonia we can titrate with NaOH. Titrated with the NaOH having molarity M, and let the titer point be, let the titer volume be, let titer volume be V1. You are ready to go for the calculations. You are ready to go for the calculations. I am not explaining the calculation. I will tell you the formula how to find out. See what all things you should be noting. Organic compound m gram treated with fusing with the sulfuric acid. The nitrogen content is converted to ammonium sulfate. Digesting an alkali, you get ammonia. That ammonia pumped into excess of sulfuric acid solution. Now this ammonia, how much ammonia came? That can be determined by the titration of the remaining sulfuric acid. If you find how much sulfuric acid remained, you can find how much ammonia came and reacted. Okay, so the remaining sulfuric acid after reacting with ammonia can be obtained by titrating with NaOH, and you get the titer volume V1 having molarity M. Then the percentage of nitrogen is equal to, I am writing the final result, 1.4 into M into 2 into V minus V1 by 2 divided by M. This is the formula. 1.4 into M. M is molarity of sulfuric acid or NaOH. V is volume of excess sulfuric acid taken. V1, the final titer volume of NaOH, and M is mass of organic compound. This is Geldal method estimation. I am referring the final formula, and we have step-by-step evaluation for deciding or deriving that formula, which we can discuss if required in the classes, or if some in-between questions are coming, which is not possible. Normally, this data will be given. You are asked to solve it straight away. Or sometimes the problem may be based on normality. The formula is very simple. Normality formula, very simple. Percentage of nitrogen is equal to 1.4 NV by M. This is normality formula. What is this NV? What is this NV? NV is equal to N1V1 minus N2V2. What is N1V1? That is quantity of sulfuric acid that you taken excess. What is N2V2? That is quantity of NaOH taken for titration. So difference between N1V1 and N2V2, that is NV. And the formula is percentage of nitrogen is equal to 1.4 NV by M. Is it clear? So estimation of carbon, hydrogen, chlorine, bromine, iodine, sulfur, phosphorus, nitrogen. Nitrogen estimation, Dumas method, nitrogen estimated as N2, and Geldal's method, nitrogen estimated as ammonia. Right? And finally, estimation of oxygen. How the oxygen is estimated? Usually percentage of oxygen calculated, very simple, 100 minus the percentage of all other elements will give you percentage of oxygen. Or you can do the estimation of oxygen by another direct method, as is given in the NCERT. You see the estimation of oxygen. Estimation of oxygen. What we do is we take a non-weight of organic compound. We take a non-weight of organic compound and we heat it, and we get oxygen and other gaseous products. All these other gaseous products we remove, and we collect the entire oxygen content we got from the organic compound, say m gram organic compound. So from m gram organic compound we got oxygen, and that oxygen passed through red hot coke. We prepare carbon monoxide, and that carbon monoxide titrates I2O5, where it is converted to I2 and carbon dioxide. So you have two reactions, A and B. Right? They are unbalanced equation. How to balance it? Equation A multiplied with 5, you get balancing. Equation 2 multiplied with, equation B multiplied with 2, you can balance it. 5 into 2, 10 carbon monoxide, 2 into 5, 10 carbon monoxide is balanced. So equation A into 5, equation B into 2, you can balance the equation. Now what is the balanced equation? First one, 10C plus 5O2 giving 10CO. Second one, 2I2O5 plus 10CO giving 2I2 plus 10CO2. Now you can understand 5O2 can produce 10 CO2. 5O2 can produce 10 CO2. That means each mole of oxygen liberated from the compound will produce 2 moles of carbon dioxide. 5 will give 10, therefore 1 will give 2. So 1 mole oxygen obtained from organic compound can produce 2 mole carbon dioxide. So 2 mole carbon dioxide obtained from 1 mole oxygen. Now you can have the calculation. 2 mole CO2 you get from 1 mole O2. 2 mole CO2 means 2 into 44 gram obtained from 32 gram oxygen. Therefore, 1 gram CO2 obtained from 32 by 44 into 2, 88 gram oxygen. Therefore, how much carbon dioxide we get? We need to take the mass of carbon dioxide obtained, let it be m1 gram carbon dioxide obtained in the experiment. Therefore, m1 gram CO2 to get 32 divided by 88 into m1, and this is obtained from m gram organic compound. This is obtained from m gram organic compound. Therefore, 1 gram organic compound, it will give you 32 divided by 88 into m1 by m gram of oxygen. Therefore, percentage will be into 100. So it is 32 divided by 832, it is O2. 88, that is 2 mole carbon dioxide. 2 mole carbon dioxide. M1, mass of carbon dioxide. M, mass of organic compound. Right? So I repeat, 32 is O2. 88, 2 mole carbon dioxide. So per mole oxygen, you get 2 mole carbon dioxide. Now what is M1? M1 is mass of CO2 obtained in the experiment from m gram organic compound. M is mass of organic compound, M1 mass of carbon dioxide. Hope it is clear. That way we can determine the percentage of oxygen, which is usually not required. 100 minus the percentage of all other elements will be oxygen. Right? And these are all traditional techniques. Modern reviews, we have sophisticated machineries where you keep some nano quantities of material. You are able to get the percentage of various elements present in the compound and almost all entire details regarding the estimation and qualitative, quantitative analysis. Right? Anyway, traditionally, these are the method of estimation of carbon dioxide. Estimation of various elements in a given organic compound. Right? It's a long chapter, as all of you know. First organic chemistry chapter, which becomes the basis of the entire organic chemistry, even when you go for future classes. Let me remind you the major topics that we have gone through in the chapter 12. Organic chemistry, some basic principles, the structural details, classification of organic compounds, functional groups, naming, common naming and IUPAC naming, systematic naming, as much as possible. Doing examples is most important. Then isomerism, structural isomerism, stereoisomerism, fission of covalent bond, homolytic, heterolytic fission, carbocation, carbanion, free radicals, electrophiles, nucleophiles, various electron displacement effects, inductive effect, plus I effect, minus I effect, electromeric effect, plus E effect, minus E effect, resonance effect, plus R effect, minus R effect, hyperconjugation, no bond resonance, and finally this purification and characterization area. A lot of discussion on purification techniques, a lot of discussion on qualitative analysis, that is detection of elements, and finally quantitative analysis, that is estimation. Right? That's all from the chapter 12. Right? We will meet with another chapter in another video. Till then, bye, take care, see you.